So our first talk this morning will be by Professor Jiro Kasahara, who is a professor at Nagoya University, and he will talk about his recent work on detonation. So help me in welcoming Professor Kasahara.
Nice to meet you. My name is Jiro Kasahara, Nagoya University. So first of all, I would like to really appreciate for inviting me to this excellent world top university course. Thank you for Professor William Robert. Thank you for Professor Dina Lacoste. And thank you for all of the CAST community members and all of them. Thank you very much. So it is my great honor to present the recent research of the detonation system level research. This is rotating detonation engines. I try to a little bit. It's okay. So rotating detonation engines flight demonstration by sounding rocket. Sounding rocket is basically for scientific measurement near the atmosphere, high level of the atmosphere or space science. But we apply this to the rocket propulsion system demonstrations. The right side is the Earth. So first of all, the detonation is a very high-speed combustions, about 2,000 meters a second, very fast combustion wave, and it is composed of shock waves and heat release, chemical reaction zones. This is a typical movie of the detonation start now. The burned gas compressed in front of the mixture, and finally, this point, the detonation starts. The very fast flame is very important to high efficiency engine and very small combustor engines. If you use these phenomena, engine combustor size become very, very small. Rotating detonation waves, just after the injector, all of the propellants burned by this very fast combustion waves. So, and these waves also generate the high pressure and high temperature. High temperature is due to chemical heat release. High pressure means easy to using a thrust, aerospace thrust. So if we control this wave, you can have very compact propulsion systems. So our strategy is making this system just the size of the 2 meter long system and demonstrate by a sounding rocket. 3 years before, we launched the sounding rocket test using gas fuel, gas oxidizer engines. And this year, liquid, ethanol, N2O, liquid propellant demonstration will be done in next August. So today we present 2 rocket engines demonstrators. Final, our goal is innovations of the rocket engine systems. Rocket engines usually very long combustor and nozzle and generate a high thrust. But if we use a detonation engine, not wrong, very small, like small arrays of the detonations. Not old style TV system. Now we have a very thin screen style TV movies. So such kind of the innovation, the detonation can occur. So this is a typical rotating detonation engine systems. So the bottom of the engines, there is a injectors. So detonation propagates 2,000 meters per second. The developing view is like that. The burn gas generates high pressures. So thrust is this directions. Waves propagate this direction, and burn gas is expand this waves. So jet is inject the upward in these pictures. So this is a high speed video here. So the detonation waves really exist like that. And the real-time movie is there. So real timing, it looks almost identical to usual conventional rocket engines. But in the high-speed camera view, detonation wave propagates in the bottom. The merit of type of the detonation engine is basically lightweight, very small, well, like plate engines, and very fast combustion heat release lengths, like 20 millimeter, very small lengths, and better mixing by using detonation waves. So not the injection impingement, but also shock waves mixing these propellants. And the wave generates a pressure, so there is no slot. Rocket engine is converging and diverging is basically, we think, but if you use a detonation, just diverging slot is possible by using this detonation waves. And of course, high efficiency is important issue, but a little bit, not a little bit, a very big difficulty. And many researchers, of course, I want to get the higher performance, but it needs some innovations and innovation techniques. And finally, heat flux is bigger than the conventional combustors, just 5 or 10 times higher in the detonation propagation regions. And the last 8, flexible structure. Such kind of a film type, the thin detonation waves, detonation engine is integrated to the gas turbine and compressor or other tank system. Integration is very new area explored by this detonation wave engine. So in the future, the completely different aerospace engine, aerospace airplane can be possible by this detonation wave engines. It is our history of this RD engine development. 2021, first sounding rocket was launched. And now 2024, the second launch. The third launch is scheduled in 2026, 2 years later, using LOX hydrogen or LOX methane. So first of all, I would like to introduce experimental test facility. Our facility looks like that. About 30 cubic meter space chamber, and the rotating detonation engine was installed inside these chambers. And the test duration is 5 seconds, maximum 5 seconds. In 1 day, 10 shots is possible. So this is typical rotating detonation engines. Oxidizer ox and methane impinging triplet injector was installed. And annular type RD was, the structure is like that. A small nozzle was installed in such a demonstrator. So this is typical thrust. This is typical, well, typical thrust histories. Okay. So detonation engines thrust is easy to calculate. It is a very typical it's a typical equation of the prediction of the combustion pressure. This is a prediction, and the point is experiment. You can easily predict the combustion pressure like these equations. So if you determine the mass flux and slot area, you can easily predict PC. That's it. And you can also, if you get the back pressure like a space, the back pressure, PC divided by back pressure about 1,000, it means a very low pressure conditions. You can calculate the ISP about 300 or over. This is all of the plot is by rotating detonation engine. It is easy to predict by using these conventional calculations. So detonation engine is not different from the conventional engines, almost the same. The almost same level of the thrust is easy to get by using this type of engine. But heat transfer is very difficult to estimate because some diffusion phenomena is dominant in this heat in these engines. So this is a prediction, and experimental data is like that. About several 10 megawatt per square meter is ordinary suffered in the detonation propagation regions. So next, the flight test is introduced. So rotating detonation engine and pulse detonation engine was tested 3 years before. The oxygen and methane was used. It is gases, fuel and oxidizer. The space flight test is very dangerous. So Japanese NASA, JAXA controls the safety switch. So if they say okay, the power was generated to our system, and we can start our sequence. The total length about 2 meters. The rotating detonation engine and pulse detonation engine for controlling the controlling a torque of the systems. At tank and avionics is there. This is a total view, rotating detonation engine and pulse detonation engine and supply system, tank and avionics. This is ground level test. So in the ground, we get many data because we're using many pressure port and temperature port and thrust stand. And we get pressure and mass flow rate and equivalence ratio like that. And we also, analog and digital camera was installed in front of the rotating detonation waves. We get the video data. So avionics development is very difficult for combustion researchers. So we get a special designated professor from MHI, and he developed the avionics. And totally system level test was done in ground. So sounding rocket, Japanese sounding rocket is basically solid rocket motor launch and stabilized by rotations. So our system also survive by rotation. So dynamic balance of the system is very important. So by ground test facility, we check the dynamic balance, and also vibration test. Solid rocket launch shock about 10 or 40 G, and aerodynamic vibrations. It is very important to check by shock and vibration test in ground. And finally, ground test training was done about 1 year before for launch, the final system. The flight operations launch after 2 minutes. Detonation engine was operated 6 seconds, and after that, 4 minutes and 5 minutes, 4.5 minutes and 6 minutes, pulse detonation engine was operated. Finally, data was recovered by a specially developed capsule. It is inflatable, like an automotive airbag, and re-entry to the atmosphere, and the helicopter recover this capsule to our facilities. So this is real rocket second stage. Our system was installed in these areas. The first stage is solid rocket motor. The second stage is detonation engines. So recovery capsule was installed in the nose cone. So, the solid rocket motor, 23-second operations. And after that, the separations, nose cone deployment and separations. And this is a rotating detonation engine operations. Now start. You're finished. This is in a space operations. Please compare the ground and space. This is a space and this is a ground test. This is a space and this is ground test after the combustion test. So ground test, there is a very strong shock waves generated because due to atmosphere. So high heat flux is generated in the top of the center body. And the data for the thrust, data of the thrust is very good matching to predictions. So acceleration and ISP is also very consistent to the predictions. The total ISP is about 300 seconds. And one of the interesting point is here, it is rotation speed is increasing during this 6 seconds because detonation propagations occurs occurs a flow. So some frictional force occurring inside the detonation waves. So not main thrust is also, of course, generated, but also small torque was generated during this experiment. So the sensor is detect this torque increasing the rotational speed like that. It is one of the interesting point. We generated two or three published this phenomenon. The next flight experiment this year, summer, we are now preparing. So ethanol and N2O was installed in these systems. So the difficulty is liquid tank ethanol, liquid tank N2O needs a pressurized nitrogen. We use a nitrogen pressurizations is a new system for us. Pressurized N2O and pressurized ethanol is installed in these systems. So it is very big difficulty for our research teams. So our collaborator, Roland Institute of Technology, gives us the systems, N2O, run tank, pressurized tank, ethanol tank. Our new engine was there. The control center is there. And liquid detonation is very important to develop a new injector hole. So ethanol injector hole is, the diameter is 0.15 millimeter. It is a kind of the limitation of the make a small hole. So this is video. So this is a high-speed view. So we do not use a center body, just a cylindrical RDE, but such kind of the detonation propagate in this areas. So it is very small pictures. I'm sorry, but this is a N2O, and this is a ethanol. Ethanol ethanol is here, and it is in liquid phase. But N2O is, if the background pressure is low, it is easy to vaporize. So the injection area is liquid, and gas phase is combination of these two phases. So impingement is here, and most of the mass is get to the near the outer wall. Detonation propagate near these areas. So some erosion, it is not a good case. Some erosion occurs in this outside of these areas. We get the movie at not only movie, vibration sensor can detect the detonation propagation speed by the frequency like that. So this is a total So in a real flight experiment, also 10 seconds or longer, the tank is vacant, is a test in the time. So maybe 10 or 15 second operation will be done in the August. And before the final flight model test, we also did breadboard model. It means perpendicular systems, engine and the tank, and same level of the supply system. It is just 1 year before. And this is also system level test. And this February and March, final pre-flight model was tested and successfully finished. This is one of the cut of the system level test. Avionics and the tank And engine supply system is here. It is Muroran Institute of Technology in Hokkaido, North area of Japan, winter test. So we have to set a heater is there. The black film is a heater. So this is our state of the rotating detonation engine. But the fundamental research is also important. So one of the important fundamental area is cylindrical, not annular type RDE, but cylindrical type RDE. There is no center core, just a hollow type, cylinder type RDE is good performance, has a good performance. If the cylindrical RDE, if you use the very small length of the combustor, you can get. And if you set such kind of a clustering, the conventional rocket engine is become very thin. It is one of the big merit to using this kind of the engines. So let's test that performance. This is maximum 70 millimeter length of the very simple cylinders. Detonation loaded these areas. And we can visualize total of the combustors like that. For example, 6 tests was done. We can check the detonation propagation or not. And the side view is like that. This is 70 millimeters, but detonation and combustion area is just a 20 millimeter. And it was 70, 40, and 20 millimeter. This the same mass flow rate. Compare the thrust, almost same. It means 20 millimeter is enough to complete the combustions. And ISP is very good. This is a theoretical prediction of the choking conditions. The choking at the outlet of the combustor, it means 200 over. All of the experiment, if you use a 20 millimeter, the ISP is 200. So the next, I'd like to show the diverging RDEs. There is no converging region, just a diverging. 5-degree diverging sections. The side view like that. Detonation propagate these areas. So please look at this picture. Combustor is here. It is just ignitions. After the several minutes, several microseconds, detonation propagates like that. And the burned gas expand these areas. Once again, it is like a DDT a little bit after the ignition system is here. Detonation propagates these directions, and burned gas is expand the right directions. From the calculations, this is an experiment, burned areas, heat release areas, and accelerate by heat release. And after the expansion area, mechanical accelerations, then finally the Mach number of the outlet is 1.7. There is no slowed, just diverging areas. We get a supersonic flow, just a diverging area. It is very new system for aerospace propulsions. And we are now collaborating with a supersonic gas turbine team of the Purdue University, Professor Paniagher, Professor Terry Mayer, and James Brown now in North Carolina State University, and Venkata Asmathanan from the Purdue University. So this type of engine and turbine integration is really new areas we try to challenge a new gas turbine system using detonation combustors. So one of the challenges is a new film cooling. So this is a holotype rotating detonation engines, and this is injected, not a coolant, fuel oxidizer injections. The size is very small, 20 millimeter, like that. The heat protection area is also small, so we can introduce to injector, not only injection, but also cooling purpose, like that. So we tested such kind of the film cooling RDE. Fuel and oxidizer is injected all over the surface inside the combustor, like that. So please see this video. This is an injector port, and this is a propagation of the wave-coupled combustions. It's not perfectly detonation, but very fast combustion was occurred in such kind of RDEs. And 5 seconds after, equilibrium temperature is reached. So we can operate very long time duration in this combustor. The highest temperature is 800 Kelvin. It is enough to operate very long durations. So the ISP is also enough to prediction. Very ideal ISP is we get in the test facilities. So most recent research, the one of the synchronized ignition of the rotating detonation engines. So we test 2 hollow RDE. Only one RDE ignited. And we make a hole between these 2 RDEs. Once the ignition by gunpowder, this RDE, just after the about lower than 1 millisecond, the next neighbor RDE was ignited. We checked the synchronized ignition was confirmed by a high-speed camera and, of course, a pressure sensor or something like that. The paper was accepted in the Journal of Propulsion Power recently. So one more rotating detonation engines, the helical RDE. It is a collaboration work with the Purdue University gas turbine engines. So not flat, the helical wave RDEs. It generates a little bit angular momentum outflow, not only angular momentum RDE, but also direction of the propagation direction can be controlled, this kind of the RDEs. So we did several times of the experimental 30, 40, now is a 50 times experiment. This like RDE generate these directions of the RDE, and negative type is generate this direction of the RDE. We confirm this kind of the, we confirm such like that. RDE direction control is difficult, very, very difficult, but now we get such kind of the technique now. So the future plan I would like to express. So now the second launch test will be next August. The third is 2 years later. And now Japanese Mitsubishi Heavy Industry and JAXA is very, very interested in this field. So the first step, very small engines, for example, retention thruster for stabilizing liquid. retention thruster is very small, and reaction control system is very small engines. It should be replaced by a RDE. It is our first strategy. And the second step, the final stage of the H3 rocket or Epsilon rocket of the solid rocket motor is a small, finally generate a small thrusters, generate the final stage. It is a second step. Then finally, we are develop a lander or orbiter of the moon or Mars. And now Japan is developing next main rocket launcher is start to developing. So the first or second stage will be replaced by the rotating detonation engines. So Professor Bohon was there. He was organized very good international workshop for detonation propulsion 2 years before. So now this field is a very young researchers come to these areas. Please come and go future with us. And I would like to really thank Professor Woransky. He was a leader during this 20 years, and I was very helped by him. And Edita was a student of Professor Woransky. And we are really appreciate you and this community, international community. And I'd like to go more forward to contribute all of the world for good futures for propulsions. Thank you very much for giving this opportunity. Thank you.
Thank you very much, Professor Kasahara. It was an amazing talk. Thank you so much. We have time for questions from the audience. Who wants to start?
Thank you, Professor, for a wonderful talk. I just have two questions. Mm-hmm. The first part is, so you showed that the rotating detonation engine, it creates non-uniform in temporally and also spatially. So how do you deal with stabilizing it? Because especially when you use in upper atmosphere, the thrusters have to be stable, right? And the second part is, so in one of your picture, the sounding rocket, you saw that the rotating detonation is used in the second stage. And usually, yeah, first stage, we use solid propellant rockets. So is it also possible to use the same liquid pop fuel rotating detonation also in the first stage rather than second?
Okay. So my first answer is so the very good questions. Ununiform situation detonation propagates, but such kind of the combustion waves accelerate the combustions. A little bit later, this area, the burned gas is almost completely finished. So vaporization, mixing, and burned process is inside of there. So this area is keeping the thrust profile is almost same. So the difficulty is including these areas. So the phenomena is very, very complicated. Please analyze with us. This is the second question. So in the near future, we would like to install the first stage of the rotating detonation engines. Now, my students developed the very small RDE system. The first stage level is now going on. It is one of the challenging areas.
Question here?
Yeah. Thank you, Professor, for the very nice talk. You were talking quite a bit about the heat transfer, the wall heat transfer, which is quite a significant thing for the RDEs, and also cooling methods.
Yeah.
So my question is, have you tested different materials for making these RDEs? Are there any special materials that you have tested apart from the conventional ones?
Yes. Now we using stainless steel and copper and film cooling many styles. But material is just two type now. But it is very important super alloy for heating problem is very challenging point, and I would like to do such kind of research.
Sure. Thank you.
Thank you.
Thank you for the talk. I was interested in thermoacoustic instabilities.
Yeah.
And there's lots of innovative designs, and that is not easy to control, of course. Is this an issue for you? And if so, how do you overcome it?
This phenomenon is basically very unstable, not a stable phenomenon. It is a very strong acoustic coupling here. And from till now, the conventional rocket suppress the acoustic vibrations, but in this RDE enhance the type of the instabilities. So the controlling method is very difficult, but it is one of the most important deep research point, I think. Yeah, it is right answer to your questions. No.
Okay, so it is an issue, but you have mechanisms to deal with it, yeah?
Yes.
Because you could use your engine in milliseconds or microseconds.
Yeah. Thank you very much.
Sorry, so I just have a general question to ask you. I don't know if this is confidential. Can we have an idea of the cost of this program, the budget for this overall study? Is it confidential, or can you tell us about the cost, the budget for this program?
Yes, of course. Budget from... Okay, total. About the なんだっけ、1億円って何ですか？1億円1 year. $10 million per year. $10 million per year.
Okay.
Yeah.
Thank you very much.
Yeah.
Thank you so much.